Good morning to one and all present here. This is Soundarara from High-Tech Engineering College, doing fourth year mechanical engineering.
I'm J. John BRITTO, studying final year mechanical in BTech Engineering College.
And this is Prakash Raj. And this is Prakash Raj R from High-Tech Engineering College. Okay, going into the topic, we have decided to choose a topic on design of heat exchanger for cooling the furnace return oil temperature. We are doing our project at North Chennai Thermal Power Station 1. We extend our arm for sincere support of the external guide Mr. E. Ranganathan and our internal guide Mr. A. Kalyan Kumar and project advisor Mrs. Gayatri and our beloved HOD for their valuable support. Moving on to the topic, these are the contents which we are going to discuss. First, we will be discussing about abstract, introduction about the company, a little plan details, introduction about our project work, a small project outline, problem identification methodology, and so on. Okay. Heat exchanger plays an important role in thermal power station. First, what is a heat exchanger? Heat exchanger is a device which is used for heat transfer from one medium to another medium, either from solid to solid or from liquid to liquid or anything. In our project, we have generated a design of heat exchanger for cooling the furnace return oil from the boiler. What is a furnace return oil then?
In the existing system, heavy fuel oil HFO is cooled by heat exchanger, which is located in between the furnace and the fuel tank. But the HFO oil is not cooled to the minimal temperature due to low heat transfer. Thus, we have designed a heat exchanger to overcome this defect. Uh, imagine that the heavy fuel is oil is not in a liquid state. It is a semi-solid, semi-liquid state. Uh,
The main purpose of our project is to cool the furnace return oil from the boiler so that we can avoid the failure or explosion of oil tank, fuel cranking, and to reduce thermal stress. We have selected shell and tube type heat exchanger and as is clear for deciding the heat exchanger in our project. A small introduction about the company. The North Chennai Thermal Power Station is situated about 25 kilometers from Chennai city. Each unit each unit generates 210 megawatt with total generation being 635 watt. The site is flanked on the east by the Bay of Bengal, west by Buckingham Canal, south by Ainur Creek, and north by Katapulli village. It is well connected by road and train. The total area is 1,107 acres for plant, 1,126 acres ash dumping, including provisions for ash slurry pipelines and 247 acres for staff quarters. Going on to the next tile, our NCTPS 1 consists of the following units: boiler unit, DM plant, RNO plant, feed water system, coal handling system, ash handling system, fuel oil pump system, chimney, generator house, and turbine. My friend Soundara Pandit will discuss the following. Okay, going on to the topic. In our project, as I said earlier, we have generated a design of heat exchanger for cooling the furnace return oil from the boiler. We have selected cylinder tube type heat exchanger and this fluid for designing the heat exchanger. The boiler furnace is first ignited with high-speed diesel oil. In order to attain the maximum temperature of 540 degrees Celsius, heavy furnace oil is passed. Once the temperature is achieved, the oil passage is stopped and bulbous cold is used continuously.
Heavy fuel oil is used to attain the high temperature required in the boiler. After that has been acquired, the oil is cut down and returned to the fuel tank. This heavy furnace oil is in very high temperature of about 100 degrees Celsius. This must be cooled down before entering into the fuel tank. The purpose of cooling the oil is to avoid the failure of explosion of oil tank, to avoid fuel cracking, and to reduce thermal stresses.
Okay, a small outline of our project. First, the furnace, for the furnace, the HFO is supplied from the fuel tank. The HFO is supplied from the fuel tank is at a very low temperature of about 30 to 40 degrees Celsius. It is in a thaw state form. From furnace, once the HFO is then sent to the heat exchanger. At this point, it is at high temperature of about 90 degrees Celsius. So there has to be a heat transfer which is done at heat exchanger. The medium used here is DM water, which is obtained from demineralization plant. The temperature of DM water is 28 degrees Celsius. Due to conduction and convection, there is a heat transfer, and the HFO oil at the exit becomes 50 degrees Celsius and is returned to the fuel tank, whereas the DM water is at 58 degrees Celsius and is returned to the condensate extract tank. Problem identification. Increase of HFO temperature at the outlet of the furnace, explosion of fuel tank and cranking. And for this, we have suggested an idea of applying a heat exchanger. Okay, once we have applied a heat exchanger, then there will be a formation of impurities and excessive transfer rate. So we have decided to go on with shell and tube type heat exchanger.
Heat exchanger. Heat exchanger is employed to cool heavy furnace oil temperature. We have selected a shell and tube type heat exchanger. Demineralized water is used to cool the HF oil. The inlet and the outlet temperature of the water is 28 degrees Celsius and 58 degrees Celsius. The inlet and outlet temperature of the oil is 90 degrees Celsius and 50 degrees Celsius as observed. The heat exchanger is located in between the HFO tank and the furnace. The water in the heat exchanger is supplied from the demineralized plant. The heated water is supplied to the condensate extract tank. Fouling factors. The substance of heat exchanger do not remain clean. After heat exchanger is in use for some time, the surface becomes foul with deposits which are formed due to impurities in the fluid and chemical reaction between the fluids. The effects of these deposits are felt in terms of greatly increased surface resistance, affecting the value of overall heat transfer coefficient.
Skipping all the, let's get okay. Some of the important design calculations are heat transfer, water outlet temperature, mean temperature difference, area, and effectiveness. These are the given values. The cool fluid used here is water. The hot fluid is heavy furnace oil. The type of heat exchanger used here is shell and tube type. The inlet temperature of water is 30 degrees Celsius. The outlet temperature of water is what we have to find out. The inlet temperature of oil is 90 degrees Celsius. The outlet temperature of oil is 50 degrees Celsius. The mass flow rate of water is 2.59, mass flow rate of oil is 3.21, density of oil is 971.8 kg per meter cube, specific heat of oil, and so on. Okay, first we are going to calculate the heat transfer. Heat transfer is given by the formula Q is equal to mH, which stands for mass flow rate of hot fluid, and CH, which stands for specific heat of hot fluid, T1 minus T2. Upon calculating, heat transfer is equal to 338.69 kilowatt. Water outlet temperature Q is equal to mc into CPC T2 minus T1. mc stands for mass flow rate of cold fluid, and CPC stands for specific heat of cold fluid. T2 and T1 are the inlet and outlet temperature of liquid. Upon calculating, water outlet temperature is equal to 58.05 degrees Celsius. Mean temperature difference. Since we have decided to calculate for counterflow, what is meant by counterflow? In the shell, the water will be flowing in one direction, and inside the tube, the oil will be flowing in the opposite direction. This is called as a counterflow. Okay, del T is equal to capital T minus small t2 minus T, capital T2 minus small t1 by ln of capital T1 minus small t2 minus capital T2 minus small t1. Upon calculating, the temperature difference is 25.53 degrees Celsius. From data book, the P and R values are given. So F is equal to 0.8642 passes. The mean temperature difference is equal to del T into F, which is 21.95. These are the area and effectiveness. Area is equal to 51.4 meters square, and effectiveness E is equal to 0.689. Sorry, epsilon is equal to 0.68. Okay, this is a comparative study
where the water inlet and outlet temperature. In existing system, it consists of 28 degrees Celsius and 61 degrees Celsius, and in proposed system, 28 degrees Celsius and 58 degrees Celsius. It has been reduced. The observation changes observed. Oil inlet and outlet temperature. In existing system, 90 degrees Celsius and 53 degrees Celsius, and in proposed system, it is reduced. Sorry. at 90 degrees Celsius and 50 degrees Celsius. Outer diameter of the tube. In existing system it is 20 mm and in proposed system it is also 20 mm. There is no change. Shell diameter. In existing system it is 470 millimeter and in proposed system we have increased it to 502 millimeter. And the number of tubes. In existing system it consists of 312 tubes and in proposed system it consists of we have increased the tubes to 328 tubes. Area. In existing system the area is equivalent to 50 meter square and in proposed system we have increased it to equivalent 55 meter square. Heat transfer in existing system is 328 kilowatt and proposed system we have increased the 340 kilowatt. The temperature difference in existing system is 19.5 degrees Celsius and in temperatures in proposed system is 22 degrees Celsius where the changes are observed.
We have done our design process in ANSYS Fluent. Upon calculating with this given, we have calculated several design calculations. This is our design geometry. The outer one is a shell and the outer one is a shell and the tubes which are passing is named as tubes. Liquid is passed through the shell and oil is passed through the tube. Okay. This is a screenshot of our design calculation and this is named as meshing and naming sections. There are 4 named sections. A which is called as cold in, B which is cold out, C which is hot in and D which is hot out. In A, cold in which is nothing but liquid, water in. In B it is water out. In C it is oil in, HFO in and in D it is HFO out. And this is a screenshot of ANSYS Fluent. Okay, upon calculating we have found out several solutions. This is a temperature ending. We can see that there is a very high temperature at the start of the tube, at the inlet of the tube, where the oil temperature is very high because it gets inside. Once it gets outside, the temperature decreases. Next, rendering of turbulence kinetic energy. You can go through it. Velocity vector by static pressure. This is velocity vector by static pressure. Volume rendering of pressure. A beautiful diagram. These are the papers we have seen. Some of the papers are Advances in Thermal Power Plant by Mr. Kriegel and D. Fly. He is our relative. And some other things. And the most important paper is by Tandetco paper. The topic of the paper is arrangement of coal to meet the requirement of thermal power plant. It is a very excellent paper we have read. And these are the basics of heat transfer. Heat transfer 8th edition is what we are going through right now. These are the work schedule and conclusion.
Conclusion. Thus, the design of heat exchanger for cooling the furnace return oil temperature is generated. This design process is suitable for cooling the heavy furnace oil. Further implementation of this design will prevent the heavy furnace oil tank explosion and reduces the thermal stresses of the HFO. Therefore, in our project, we have solved explosion problems of the fuel tank in the thermal power station and have reduced the unnecessary problems of the fuel tank, thus improving the fuel tank life. Thank you.
Thank you. Any queries?